I love the bungee jump question. It is hard. I will admit it's a hard question. It tricked me a few times, it tricked my friends, and it does get very difficult to solve unless you basically draw your picture correctly. I'm going to try and go through and solve the bungee jumper question now. The basic gist of it is, as you fall, you pick up kinetic energy because your gravitational potential energy goes down, your kinetic energy goes up. But then as you fall to a certain point, the bungee rope starts to stretch. So it's stretching from this point to this point here. As it's stretching, the spring potential energy is going up, and therefore your kinetic energy is going down. And the complicated thing is, while the spring potential energy is going up and your kinetic energy is going down, your gravitational potential energy is also going down. So we've got three different forms of energy being exchanged all at once. So for the purposes of this question, the first picture shows the person about to jump. The second picture shows the person at the point where the rope starts to stretch. And the third picture shows, this is important, the point where the person comes to a stationary stop. So the person comes to a stop, they are stationary. So at this point here, they're still traveling down with some speed. At this point, speed is zero. And that's important because if speed is zero, kinetic energy is zero. So we've only got really two forms of energy at play. To set up this question, I'm going to put in a few numbers. First of all, this person is 2 meters tall, and their center of gravity is halfway between their head and their feet. So their center of gravity is 1 meter high if they're standing up. Secondly, the length of the unstretched rope here, so I'll just draw a dotted line, is 20 meters. And the third thing I'm going to set for this first question, I'm going to do 2 or 3 videos on the bungee jump. The third thing I want to show is that the person comes to a stop when their head is 30 meters below the platform. And the end goal is to find both the kinetic energy of the person at this point here and the K value of that bungee cord. So the bungee cord behaves like a spring. The force it exerts is equal to K times the extension being from this point here to this point here. And the energy stored in it is given by that equation up there. The energy stored is half K times the extension squared. Let's solve for the kinetic energy at this point first, because it forces us to really think about how far this person has fallen. When we're talking about H here, so we're going to be dealing with delta UG. What was the change in gravitational potential to get to that point? Because spring potential has not yet come into it. The rope has not yet extended. That is the point where it begins to extend. So we're only going to look at the change in gravitational potential energy, because it means that as gravitational potential energy goes down, kinetic energy goes up. That's the same for any falling object. A rock being pushed off a cliff will behave similarly to this person. But when we look at change in gravitational potential energy of an object, we say it's the mass of that object, say there's a rock, multiplied by the gravitational constant times delta H. Now if the rock is pushed off a cliff like that and it hits the ground down here, we can basically say that was the change in height there. But what we're really saying is that the change in height of the center of gravity was equal to that distance there. Can you see those two arrows are the same length even though I'm drawing them from different points? Since the rock doesn't tip over anything as it falls down, if we take the bottom of the rock here and the bottom of the rock here and we calculate the distance between them, That's the same as the center of the rock here and the center of the rock here. Try to understand that. Now, at the point where the person is falling and we want to calculate the kinetic energy, we need to know how far the center of mass of this person has fallen. If the rope here is length 20 meters, or the cord, the rope and cord, I use that word interchangeably. But if the length of the rope is 20 meters and the center of mass started off at that height and finished at that height there, what is that distance there? Because that is actually delta H. Well, if I fill in some values, it might clue us in. Let's fill in the fact that the center of mass here, that distance there is 1 meter, and the center of mass down here is 1 meter below the end of the cord. So we see the total length that the center of mass has fallen is 1 meter plus 20 meters plus another 1 meter. So delta H is equal to 22 meters. Have a look at that. Even though the length of the rope is only 20 meters, since the person has effectively toppled over like that, the total fall of the center of gravity is 22 meters. So 20 meters of rope, 22 meters of fall. And we'll find here it's a little bit different because we're not measuring the rope, we're measuring the distance the head has fallen. But first of all, let's focus on this first change in gravitational potential. So delta Ug is equal to mass. The mass of this person we'll say is 80 kilograms. Sorry, I forgot to mention that. Delta Ug is 80 times 10 times, well, the change in H is actually negative 22 since it's going down. So now I get an N total of 17,600 joules. And at that point there, the spring potential is 0. So all the gravitational potential that's been lost, which is equal to, negative 17,600, is going to equal the change in kinetic energy. And since we're assuming the person didn't start off with any kinetic energy, they've just sort of toppled themselves over, we can say that the final kinetic energy at this point here is equal to the initial 0 plus 17,600. That's 17,600 joules worth of kinetic energy. So kinetic energy at that point, 17,600 joules. I'll shrink this down to give us room for our next operation, finding K. So we have these three forms of energy: kinetic energy, gravitational potential energy, spring potential. In the first part of the fall there, the gravitational potential energy becomes kinetic energy. As the spring, as the rope or bungee cord starts to stretch, gravitational potential energy becomes spring potential, and since this person is obviously slowing down, kinetic energy also becomes spring potential. Like that. So as they're dropping, that's the case. And then as they reach the very bottom of their drop, we end up with a completely depleted kinetic energy. So that's 0. And all of the gravitational potential energy has become spring potential energy. So this is the key part to this question. When the bungee jumper reaches the bottom of their jump, all the gravitational potential energy that they've lost on the way down, given by that change in height there, has gone to spring potential. So let's figure out exactly how much gravitational potential energy they have lost. Delta Ug is equal to mg delta h. How far has this person fallen? Now it's 30 meters from the platform to their head. That means there is also 30 meters from their old center of gravity to their new center of gravity. You can see that this line here and this line here are actually the same length. So this end is 1 meter higher than this end. That's a 1 meter gap there. And this end up here is also 1 meter higher than this end there. So delta H is in fact equal to 30 meters. Therefore, the total change in gravitational potential energy is 80 times 10 times 30, which comes to 24,000 joules. That must be, if we are claiming that all the gravitational energy has turned into spring potential, that must be also equal to the spring potential in the bungee at that point there. The cord has absorbed all the gravitational potential energy that's been lost. US, or spring potential energy, is equal to a half k x squared. So we have a great equation, 24,000 joules is equal to a half kx squared. We want to find k, but since there are two unknowns in this equation, it's not possible right now. What we need to know is how far that cord has stretched. What is x? Since x is equal to the extension. So this is, as I said in the beginning, one of the important parts of this question where you need to have drawn a great picture. If you've been given these three pictures here, we at least need to label it properly. What is the difference in height between the bungee cord there and the bungee cord here? Well, we know this bungee cord here is equal to 20 meters in length, and we know this length here from platform to head is 30 meters. That must mean if the person is still 2 meters tall down here, they don't change height, the length of this bungee cord here is 30 minus 2, or 28 meters. So the bungee cord has gone from 20 to 28 meters. That's an extension of 8 meters, dealing with meters in this equation here. So now we have 24,000 joules worth of energy must be contained in a spring that's extended 8 meters. To get k by itself from here, we say 24,000. We can multiply that by 2 to get rid of the half there, and divide it by 8 squared, that's divided by 64. And we find k is equal to times 2, 750 newtons per meter. Newtons per meter being the units for k. That's the question solved. The number one mistake that I see people making with this question is that they calculate the kinetic energy of the person at this point here. And they say, oh, okay, they have 17,600 joules worth of kinetic energy, and the spring takes that away. So they write this. The spring potential must equal 17,600, so a half kx squared is equal to 17,600. They ignore the fact that gravity is still acting on the bungee jumper between this moment here and this moment here. So even though the kinetic energy of the person is 17,600 joules here, by the time they get to the bottom, if there were no spring, the total kinetic energy would actually be 24,000 joules. And that is what is being impeded by the spring. So don't forget to add the last little bit of gravitational potential energy caused by that drop there. That's enough for this video. In the second video, I'm going to try to up the challenge of this question even more.